So good afternoon to the second session of our FDP webinar, and now we have the talk by Professor Chandana Ratha Madam from IIT BHU and my friend at MSc, and she will be talking about structure, John Taylor distortion, optical and magnetic properties of transition metal doped GDMnO3 material compound. So I request Samita Madam to introduce our speaker to all of you. Samita Madam.
Okay, madam. Okay, madam. Good afternoon to all of you. Myself, Dr. Samita Patnaik. It is my immense pleasure to introduce Dr. Chandana Ratha from IIT BHU, Banaras Hindu University on behalf of the Department of Physics, OUTR to FDP on quantum transition from ions to cosmos. She is an associate professor in the School of Material Science and Technology at IIT BHU. She completed her PhD from Utkal University, Bhubaneswar, and postdoctoral research fellow at University of Girona, Spain. Her expertise is in the field of nanomagnetic, dilute magnetic semiconductor, multiferroic, ion irradiation, semiconducting structure, nanostructure material, ceramic, glass composite, etc. She has made significant contribution in the field of nanostructure material, ferrites, chromides, and dilute magnetic semiconductor and their applications. She has received many distinctions such as Women Achiever in Science, Technology, Engineering and Mathematics 2021, MRSI SI Medal 2015, and Young Research Award in 1998 Material Science at International Union of Material Research Society, India. She has published around 100 publications in international journals with citation of more than 300 for two papers among them. So let's welcome Professor Chandana Ratha ma'am to deliver her talk.
Thank you, Samita ma'am. And thank you, Dr. Babita, and head of the department of OUTR. Let me share my slide. Is it visible?
Yes, madam.
So, good afternoon, all of you. Thanks a lot for giving me this opportunity to deliver a talk before you. The title of my talk is Structure, Yantala Distortion, Optical Magnetic Properties of Transition Metal Doped GDMnO3. Outline of my presentation is like I will discuss about the perovskite material and Yantala distortion, magnetization, reversal. Experimental, how we synthesize this material and characterize through exactly same photoluminescence magnetic measurements. And results and discussion, we will discuss about this phase and structural transformation, how we get this enhancement in Néel transition temperature, magnetic switching with applied field, spin reorientation transition. These are few features which we observed in these materials. And finally, I will give the conclusion with the important finding of this work. Perovskite material are in fact important from basic research and potential technological applications. One important characteristic is its ability to accommodate significant structural distortion without structural symmetry vanishing completely. An ideal perovskite structure tolerance factor is one can determine, which is T equal to 1. It is an ideal perovskite. If we will have, in fact, in practically we don't get ideal perovskite. So if it is not ideal, then how much T can vary so that one can get a stable perovskite structure? That is T between 0.89 to 1.02, one can have a stable perovskite structure. But in case T varies less than this value 0.9, then what will happen? That there will be a orthorhombic unit cell enlargement and it induces structural deformation. So structural deformation in fact occurs in these compounds, and it is due to asymmetry in MNO bond lengths and tilting of an MNO6 octahedra. So this structural distortion can be driven by the chemical composition. One can vary different composition in a material. One can vary the temperature and one can vary the pressure so that one could able to achieve this structural distortion. And how it will this structural distortion manifest in the material, that is it will give a displacement of polar cation. It can have a rotation of BO6 octahedra, which generally results in ferroelectricity, and also you can have Jahn-Teller distortion of BO6 octahedra. So this Jahn-Teller distortion in fact is a very prominent feature in this perovskite material, and this depends on the cations occupying tetrahedral or octahedral sites, which leads to splitting of T2G EG orbital. Mostly JT distortion is significant in octahedral environment. And how one can visualize this or estimate this JT distortion? One can do XRD. From XRD, Rietveld refinement, detailed studies, analysis of the XRD data. From EXAFS also one can find out this JT distortion. From Raman spectra one can see this, and of course we have shown this JT distortion from luminescence spectra, photoluminescence. So Jahn-Teller distortion, in fact, it is observed in an electronically degenerate state. When a nonlinear molecule undergoes distortion, it is to remove the degeneracy, one should have lowered the symmetry, and thus by lowering the energy. So if it is a degenerate state, then orbitals are said to be asymmetrically occupied and hence get more energy, and that energy has to be, extra energy has to be taken out so that it will go to the symmetry, lowering the overall symmetry of the molecule, and that undergoes distortion and known as Jahn-Teller distortion. So electronically degenerate state, that availability of more than one degenerate orbitals for an electron is said to be electronically degenerate state. So in this condition, the degenerate orbitals are said to be asymmetrically occupied. So for example, if you look at the figure here, this is only one electron in D cell. So you have XY, XZ and YZ orbital. This electron can occupy this or XZ or YZ. So all these possibilities there. However, if you have 3 electrons, then there will be no possibility. Only one arrangement of D3 configuration is possible according to Hund's law. So that gives in this case, you will have a electronically degenerate state. The JT effect is mostly observed in octahedral environment, and theoretically the electronic degeneracy in octahedral symmetry is possible in all the configurations except D3, D8, D10 and high spin D5 and low spin D6 configuration. However, considerable distortion are usually observed in high spin D4 state or low spin D7 and D9 configuration in this octahedral state. So if you look at here, you will have the T2G, 3 all are in the same energy. However, if it is a octahedral without any distortion. If you have a distortion, then you look the XZ, YZ is at lower energy and XY is at higher energy. So if when there is a distortion, then it will give rise to a distortion in their bond length and it will change the structure from octahedral to tetragonal also. So because this JT distortion is usually significant for asymmetrically occupied EG orbitals, they are directed towards the ligands and the energy gain is considerably more. So one can expect this distortion in case of high spin D4 or low spin D7 or D9 configuration. This is just the pictorial representation of without any distortion, where you have without distortion, and when there will be jet distortion, like you have D3, 4 electrons are there, one can see this electron can have the lower energy, and it will shows a Young-Taylor distortion, and the structure is deformation occurs. So there will be a structural transformation. So perovskites mainly we are discussing about rare earth manganites. These rare earth manganites like LaMnO3, GDMnO3, dysprosium MnO3, terbium MnO3, all these are of rare earth manganite category. And this material are very useful in different applications like photocatalysis, magnetic refrigeration, spintronics, magnetic memory, data storage, magnetic switching, magnetic sensor. You can see some of these features we also observed in this GDMnO3 system. Gadolinium manganite is like MnO6 is the octahedra, which is the basic building block in this perovskite. It has a orthorhombic structure. It can have O-type orthorhombic where C by root 2 is less than A less than B, or O-type orthorhombic where A and C by root 2 is in between A and B. It has a band gap of 2.9 electron volt. Nil temperature is very small, like very low, like 42 Kelvin. It has a weak ferromagnetism below 25 K due to the Canton antiferromagnetic ordering of JD3 plus occurs at 8 K. So this is 42 K is nil transition, above 42 it is paramagnetic, below 42 it is antiferromagnetic. When it is antiferromagnetic around 8 K, you will one can see the canted antiferromagnetic ordering gives rise to a weak ferromagnetic behavior in this system. So this gadolinium manganite, when you will dope, one can tune the band gap, one can change the stability of the structure, you can tune the magnetic transition. That's what we are going to show some of the results in doped GDMnO3 in the next few slides. So these are some of the literatures. One can see the multiferroicity and phase transition in TM substituted GDMnO3, structural magnetic dielectric studies in GDMnO3 yttrium doped. There are a few results which shows the sodium doping on microstructure, lattice distortion and magnetic properties of GDMnO3, single crystals. Some results show the tunable magnetic phase transition in dysprosium manganite with iron doping. So there are few more results are also there, which I have just listed here. The Zt active manganese 3 plus ions, which will have a T3E1 state like octahedral degeneracy, are of great interest due to the highly anisotropic configuration of MNO bond lengths as well as orbital ordering. With or without addition of dopants, it exhibits complex magnetic structure, metal insulator transition, exceptional magnetoresistance, multiferroicity, etc. Such properties are outcome of complex interplay between spin, orbit, and lattice. When we dope chromium, some paper shows that doping chromium in GDMnO3 due to Zt inactive element, chromium 3 plus is Zt inactive, and magnetic properties can be modified as oxygen octahedra is more symmetric. At the same time, when sodium, yttrium, iron doped in Mn3 plus site, it modifies the magnetic properties in GDMnO3. And iron dope, when it is greater than 0.4, shows presence of TSR spin reorientation transition. Dopants show the compensation temperature, negative magnetization when doped in GDMnO3. These few results are I have listed here, which is our results. So how we did this work, we synthesize this material, we take like rare earth nitrate and we add manganese chloride to it, and we add the citric acid and heated at 80 degrees centigrade. It form a gel, and when we dry it at 100 degrees centigrade, then it converted to powder form. After calcination at different temperature, we could able to get different concentration of dopant, and that ratio of cation to citric acid is 1:1, and calcination done at 1100 degrees centigrade for 4 hours. And we have taken chromium concentration. This is chromium 0.1, 0.2, 0.3, and 0.4. Iron concentration will vary from 0.1, 0.2, 0.3, and 0.5. So all this material which we made after doping, and then we examine its effect of dopant on structure, magnetic and microstructural properties, and we characterize this material with XRD, SEM, Raman, photoluminescence and magnetic measurement. So let us see this GDMNO3 when iron is doped from 0.1 and 0.2. This is 0, it's a pristine sample. One can see the XRD spectra where one have all this orthorhombic structure with space group EBNMA. And we made it fitted with Rietveld refinement, and we didn't see any impurity phase present up to 0.2. This is the Rietveld refinement, all these parameters we listed in the table. One can see ABC parameter, alpha, beta, gamma, and volume, which I have marked in red. It is, you can see it is decreases with increase in iron up to 0.2. From 231.22 to 230.60. And then other features like A minus D parameter, it is also decreases. Then cos square theta, which is also it is cos square theta increases. This W, this angular angle, the angle between MNO is also decreases with increase in iron concentration. So what these results in fact indicate that the structure is fitted to O prime type ortho. 2 is less than A less than B. So up to 0.2 we observe the orthorhombic structure with O prime type. And then one can calculate this Jet distortion sigma Jet with this formula, concentration of iron, this Jet distortion is decreases. Iron which we are doping, it is not active, Jet active element. So obviously from 0.2 where it was very high in the pristine sample, the sigma Jet, then it decreases to 0.08. So this O prime type orthorhombic structure is established irrespective of iron. Then volume decreases with increase in iron concentration. Why this volume decrease? That could be Mn, that one can find out the reason behind this. Then Mn3 plus iron 3 plus have similar ionic radius. So one should not expect any change in the volume because we are replacing, we are doping iron. So we expect that iron should dope on the Mn side. However, there is a decrease in volume. So that decrease in volume could be due to the presence of Mn4 plus, which has having ionic radius less than the Mn3 plus 0.53, or due to the reduction in MNO bond length. So that one has to find out the presence of Mn4 plus through other technique. And then other features which we observe is cos square theta correlated to tolerance factor T shows more symmetrical structure with increase in iron concentration because it is decreases. The cos square theta is increasing. Cos square theta is increases. And A minus B is observed and W, the deviation in MNO bond length decreases. That also indicates the symmetrical structure with increase in iron concentration. So overall we observed that with increase in iron concentration, a more symmetrical structure is observed with doping non-Jet element like iron. So this is the with Vesta plot. One can visualize these atoms in the Na unit cell, and this average MNO bond length, which is 1.93. There is a deviation from this bond length, and they reveal a strong Jet distortion. Then we, to confirm this Jet distortion, we did this Raman spectra. One can see there are 4 main modes in Raman modes we observe, which is AGT and AGT. These are transverse mode, and this is of Jet distortion due to Jet distortion, and this is also 610 is also due to Jet distortion. So 4 Raman modes like 270, 374, 87, 504 and 610 we observe. Jet distortion observed due to 487. This one is 487, and this is which is asymmetric stretching mode, and 610 is symmetric stretching of basal oxygen of octahedra. Both these modes are indicating the Jet distortion. So one can see this with increase in iron concentration, all these modes position doesn't change. However, there is a change in the broadening of this. The intensity is suddenly drastically reduced with increase in iron concentration. You can see this curve where the jetty in this peak is the intensity is small. It is up 200 to 300 nanometer in all these samples. So next we did this for X-ray photoelectron spectroscopy to determine the valency of manganese, because we have observed a feature like volume is decreases with increase in iron. So that could be due to manganese 4 plus, which is less ionic radii. That's why we did this X-ray photoelectron spectroscopy. One can see this peaks at 641.3 and 642.8 is corresponding to Mn3 plus and Mn4 plus. So one can see both these Mn3 and Mn4 plus are present. So that's why the presence of Mn4 plus in fact indicate the decrease in the volume. And with increase in iron concentration, Mn4 to Mn3 increases from 0.35 to 0.7, and that indicate the decrease in jetty distortion, because Mn4 plus, presence of Mn4 plus will reduce the jetty distortion, because Mn4 plus is not jetty active. So according to Mn4 plus, when it is increases, one half oxygen vacancy should be there, and the OB by OA decreases from 1.95 to 0.63. Here we didn't, this is the oxygen spectra. In fact, both this one is due to oxygen lattice and another is the surface oxygen. So when we take the ratio, then what one indicate that how much it is how much oxygen vacancy is produces. It is just the normalized, we have normalized OB to OA, but not exact quantification of oxygen vacancy. But there is an indication of oxygen vacancy with presence of Mn4 plus. Then we studied this magnetic behavior. We did this magnetization versus temperature, where one can see that at 50 Oersted we have taken the field cooling. Field cooling means we cool the sample with presence of 50 Oersted up to 2 Kelvin. Okay. So that is field cooling, and zero field cooling means we cool the sample without applying any magnetic field. So both FC and ZFC curve shows there is a bifurcation starts from around 40K. Okay, it is not visible here. So there is a bifurcation clearly indicate at 50 Oersted in this pristine sample. As we increase this splitting in this bifurcation, the magnetization difference between ZFC FC, you can see this is in fact increases, and in 0.2 it is very high, the difference 3 to 0.5. Here it's 1 order magnitude less in pristine sample. When we increase the applied magnetic field, then one can see there is no bifurcation, which is expected, of course, and very small bifurcation one can see at lowest temperature. In higher the iron concentration, there is no bifurcation, both the ZFC FC curve merged. So this bifurcation indicates the paramagnetic to anti-magnetic transition, and that is called Néel transition, and Tn is found to be 42 in case of pristine, and it increases with increase in iron concentration to 80K and 84K. So with increase in iron concentration, we could able to increase the Néel temperature. So when other feature, one cannot see anything else from this figure. That's why we go for the 1 by chi, like inverse of susceptibility we plot both ZFC FC. One can see here the bifurcation starts from Tn, and there is a slope change at 2 different temperature. One is we have written as T2, another is T1. So there is a slope change in T2 and T1, and this T1 is the lowest, the kink at minimum magnetization position, one minimum chi that corresponding to this ZFC peak. And this is T1 and this is T2. T2 shifts from 22 to 28 and 31K. In all this feature, one can see all this temperature T1, Tn, T2 and T1. There is a slope change at two different temperature. And T2 shifts from 22 to 28K, and then it is approach 31K, which represents the ordering of manganese. So, and T1, which remains almost same 5 to 7K for all samples, it represents the ordering of the gadolinium. At lower temperature, this rare earth element they order, and at higher temperature at T2, manganese ordering occurs. So this we could able to, other features we could able to see when we plot the 1 by chi versus temperature. But from ZFC we could not see any other thing except there is a peak which is representing like some of the feature one can indicate that the ZFC bifurcation indicates it may be a spin glass, cluster glass or super paramagnetic behavior. That we will like discuss later. Then from inverse susceptibility temperature, the other feature we also estimate like what is the magnetic moment. We fit it with Curie-Weiss law, like 1 by chi is T minus theta by C. And from that we can find out this Curie constant and theta, that is Curie temperature. So these values are mu effective, which is observed, which is calculated from the value C is 7.5 for pristine sample. As we increase, it is increases 9.47 and it is 8.63 for x equal to 0.2. And mu effective we can calculate the theoretical value one can calculate by calculating the individual gadolinium and how much manganese and it is not chromium, it is here iron. Sorry, this is a mistake. So that one can calculate, and it is 7.36, 9.0 and 8.2, which is almost matching with the experimental value. 7.36 it gives 7.5, 9 it gives 9.47 and 8.2 is 8.63. So our theoretical prediction, theoretical magnetic moment is well matched with the experimental value, which is we calculated from the fitting. And the negative value of theta in antiferromagnetic interaction between the atoms. So all are negative. That shows the strong antiferromagnetic interaction in this material. Then we did the magnetization with magnetic field. One can have with increasing magnetic field, one can see how it behaves with magnetic field. We see that at 20 Kelvin, above 40 it is paramagnetic, so we choose one temperature below 40. So in 40 it is showing the there is a slim loop, and that shows the weak ferromagnetic behavior, and both these x equal to 0.1 and 0.2 both have the like these are 2.1 and 0.2 are showing similar magnetization, and the pristine sample it is high magnetic moment at 20K, and at 4K it shows higher the more magnetic moment in pristine sample, but all are showing a weak ferromagnetic behavior at 20 and 4K. So these are the parameters which we calculated from this hysteresis loop. At 4K it is 5.45 Bohr magneton, and as we increase it decreases to 3.4. And in fact coercivity was just the opposite, which is like magnetization decreases here at both the temperature, and coercivity increases with increase in iron concentration. That indicates that with increase in iron concentration, the moment which is decreased, similarly the coercivity increase, because it shows very strong antiferromagnetic interaction. So in order to demagnetize them, you need very high field. That is the reason with increase in iron concentration, the antiferromagnetic ordering is increases, and that gives high coercivity. So as I have indicated here that there is a feature, this bifurcation ZFC can indicate spin glass, super paramagnetic or cluster glass behavior. That one can has to confirm To confirm it, we have done the AC susceptibility measurement with frequency. At 4 different frequency, 31, 101, 299 and 501 hertz, we measured the susceptibility. This is AC susceptibility measurement, and with field 3 Oersted, very small field we apply, and then one can see this is the inset where one can see all this with increasing frequency, this TF in fact increases. So that this is the dispersion behavior indicate either it can be a spin glass or cluster glass behavior. So that has to be further confirmed from different kind of laws. Like there are 3 different laws which has to be fitted with this curve, and one can confirm this. So there is in all these samples we observe a dispersion behavior. The T1, T2, the intermediate anomaly one can see also here, which we could not able to observe in M versus T, rather 1 by chi we could able to find out this intermediate temperature T2, that also could able to see from AC chi measurement. So shifting in TF is observed, spin glass behavior may be present, and that phi, one parameter which we calculate, that is delta TF by TF into log omega, is the frequency, and this phi value can indicate whether it is a spin glass or cluster glass. So this phi is found to be 0.02, 0.01 and 0.01 for all these samples. But for spin glass, the range of phi should be 0.005 to 0.08. So it indicates that this phi value is within the range of spin glass. So it may be spin glass behavior. Then we fitted this AC chi data with Neil-Arrhenius equation, Vogel-Fuchs equation, and power law. In Neil-Arrhenius, tau naught e to the power EA by kBt, and Vogel-Fuchs it is tau naught exponential EA by TF minus T. Not TF is the freezing temperature, spin freezing temperature, and power law we fitted with tau naught TF by Tg minus 1. Tg is the spin glass temperature, where tau naught is the time constant corresponding to the characteristic frequency. EA is the activation energy, and Kb of course the Boltzmann constant. So these are the fit. We have fitted all these parameters, and the fitting parameters one can see. The Neil-Arrhenius, which shows this tau naught value, is 1.37 in 10 to the minus 27, minus 28, minus 20, which is very unphysical value. So Neil-Arrhenius behavior is not well suited to these samples, because it doesn't show any physical parameter, which is very unphysical value, 10 to the minus 27. Then from Vogel-Fuchs, one can see it is around 10 to the minus 12, minus 13. And from power law, it is minus 9, minus 12, and minus 11, which is the flipping time of cluster glass is 10 to the minus 9 to minus 6. So presence of this shows this spin glass behavior. Exponent of Z nu are found to be in the range of reported value of spin glass. So all these Vogel-Fuchs and power law indicate that all these samples are showing a spin glass behavior, for which there is a peak in ZFC behavior, and that spin glass behavior could arise because of this 2 different kind of magnetic element like Mn3 plus and Mn4 plus. So there is possible interactions, could be Mn3 to Mn3 or Mn4 to Mn4 or Mn3 with Mn4. And these interactions compete with each other and could show the spin glass behavior in the present case. Then when we increase this iron concentration from 0.3 to 0.5, we see very unusual behavior. So this is the XRD pattern which we fitted with reed field fitting, and this is same orthorhombic structure without any impurity phase we observed. Then this is the Weierstrass plot where we can see there is a change in the bond length from the average value. And this is the structural parameter from reed field refinement. One can see again the volume which further reduced when x equal to 0.5 and 0.3 compared to 0.2. And there was, it is O prime type orthorhombic structure. However, in 0.5, when it is increased from 0.3 to 0.5, then it shows O-type orthorhombic structure. So we observe with increase in iron concentration, there is a transformation from O prime to O-type orthorhombic structure. And volume is further decreased with iron concentration, and jetty distortion further reduced with at 0.5 it is 0.05, in 0.2 it was 0.09 and 0.08 and then 0.05. So all these feature well explained previously, and further we increase in iron concentration, this A minus B is further reduced, and this volume also reduced. So that volume reduction, now one again see what happened, whether Mn4 plus or what else is the reason behind when X equal to 0.5. So we did this XPS, and one can see there is Mn4 plus and Mn3 plus, both are present, and the ratio of Mn3 to Mn4 is 1.34 in 0.3, and when it is 0.5 it is further increased. So this peak position corresponding to Mn3, Mn4, area under the curve increases with iron concentration, indicating presence of more number of Mn4 plus. And this ratio, of course, increase with increase in iron concentration from 0.3 to 0.5. And here we did this, earlier we could not able to do this iron spectra because iron concentration is very small. But in 0.3 we did the 0.3 and 0.5, we checked the iron, whether it is iron 3 plus or iron 2 plus. So when Mn3 is Mn4 plus, so there is a possibility of iron 3 to iron 2 plus conversion. So that we checked in higher concentration of iron. For 0.3 and 0.5 we did iron spectra, and one can see both the iron 2 plus and iron 3 plus are present. Iron 2 to iron 3 plus is 1.02, and in 0.5 it is 1.39. But peaks at 710, 713 corresponding to iron 2, iron 3 plus, and that decreases when iron concentration increases. So as this is oxygen spectra, obviously there will be oxygen vacancy because we have Mn4 plus. So that we did oxygen OB and OP peak OB to OA ratio, which decreases with increasing iron concentration. So decrease in oxygen vacancy confirms that Mn4 plus dominates over iron 2 plus. Though there is presence of iron 2 plus is there, but Mn4 plus is higher. That's why the volume is decreases, and oxygen vacancy is also decreases. So the lattice volume is decreased with iron concentration due to Mn4 plus. Again, we did this jetty distortion confirmation. One can see 0.3, it is again reduced in 0.5. That shows the further reduction in jetty distortion. And from morphology, we could able to see that there is the size is 100 to 200 nanometer. That jetty distortion also we visualized for the first time from photoluminescence behavior. That one can see it is the excitation. We did the excitation of this material at 200 nanometer. These are the emission spectra, and one can see the this inset pattern here. There is a 287, there is a 286 nanometer in pristine sample was present, which is completely absent when it is X equal to 0.5. So this emission peak at 286 nanometer shown with shaded area is found to be absent, and that is correlated with reduction in jetty distortion. That is a direct evidence of jetty distortion when it is 0.5. And we did this energy band diagram because manganese 3 plus and manganese 4 plus both are present. So manganese 3 plus has T2G and EG both the bands, and Mn4 plus is having T1G, T2G and all A1G. So these are the bands which when we excite at 200 nanometer, the electrons jump from ground state to this Mn2Tg band, and it is at the same energy level of Mn4 plus. The electrons go to the Mn4 plus energy level and come back to the ground state with these 3-4 different kind of emission peak which we observe over here. So these emission peaks which we observe because of this, both the energy levels are similar in Mn3, Mn4 plus. So when it is come back to the ground state, it is come back through the Mn4 plus energy state. So 4 distinct charge transfer bands are produced, such as 3.5, 4, 8, and 8.5, which we observe in the emission spectra. Mn4 plus energy levels realized according to the TS diagram for 3D configuration in octahedral symmetry. Then we go for this magnetization measurement. In point 3, again we see this spin freezing temperature TF at 500 Oersted, and this is for 0.5. There is a bifurcation exists. And when we plot this 1 by chi versus t, then one can see all these features is also visible, but the slope which was very distinct in point 2, it is not very distinct. So as we increase this iron concentration, Tn is of course there, which is enhanced almost up to room temperature, and T1 is remain same, but this canted antiferromagnetic T2 is 22K and 5K. So T2 and T1 shift from 34 to 9.8K at x equal to 0.3 to 37K and 10K when x equal to 0.5. Okay, so 34 to 37 it is T2 is increasing, but T1 is almost the same in both the cases. Then this is the new feature which we could able to see when we increase this iron concentration. That this feature could not able to see in just magnetization behavior. We just subtract MFC and MZFC and divided by MZFC. One can see this clear feature of spin reorientation transition. This is the Tn, we see is a clear peak, and again it decreases and it shows a spin reorientation transition at this temperature, and that is clearly visible in both this 0.3 and 0.5 case. Although in 0.3 it is not very well visible, but in 0.5 with this peak and this minima, which is spin reorientation. So this spin reorientation transition, which is at 270 and 253K per 0.3 and 0.5. Temperature decreases, but it is clearly visible, which is not reported earlier. So Tn is increased from 286K at 0.3 to room temperature when x equal to 0.5. So TSR is found to be 270 and 253K for x equal to 0.3 and 0.5 respectively. Then we did this magnetization magnetic behavior at different temperature. You can see clearly there is a clear ferromagnetic behavior in case of 0.3 and 0.5. The loop is completely open at low field, and then one can see this ferromagnetic behavior at 4K. As we increase, the magnetization is decreases, which is expected. Then we see this, did this to find out whether what kind of spin glass behavior or not. In point, as we already confirmed that it is spin glass behavior, so we didn't go for this frequency dependent SECI measurement. Rather, we did another measurement which also confirmed the spin glass behavior. Here we did the remnant magnetization measurement. What does it mean? We take the sample and cool it to low temperature at 50 Oersted field. Then at low temperature, we just take out the field and leave the sample as such for a certain time period. And we see the decay behavior of this remnant magnetization, how it behaves. So, so that means we cool the sample with a field and we just leave the sample at low temperature without any field, then we see the decay of behavior. So this remnant magnetization behavior is fitted with power law MT equal to M0T to the power minus B, and this remnant magnetization follows the power law in both the sample, which confirm the spin glass behavior. So in up to 0.5, we observed that all the samples show the spin glass behavior, and Tn is increases with increase in iron concentration, and there is a transformation from O prime to O type orthonormic structure, and all these features are well confirmed with the, taking the complementary techniques. Like with XRD, we have taken Raman, photoluminescence, and XPS. Then we did all these magnetic measurements to confirm this spin glass behavior through different techniques. So this is the conclusion. With increasing x from 0 to 0.5 along with the reduction in lattice volume, we observe the structural transformation. Raman spectra confirm a significant reduction in jetty distortion due to decrease in intensity of asymmetric stretching. Emission peak shows the disappearance of this emission peak with shows the reduction in jetty distortion. PLXPS both confirm the presence of Mn4 plus, and then while Tn increase with iron doping, TSR decrease distinctly. The mixed vacancy of manganese was contributed towards spin glass behavior observed in both samples. So this is of iron. Oh, how much time I have? Can I go for the chromium doping?
Madam, 15 minutes.
So let us flashback, not very elaborately, but I will just show the what happens in chromium doping. So this is the feature which we have already discussed. There is O prime type orthorhombic structure up to x equal to 0.3, and O prime to O type orthorhombic structure transformation occurs when x equal to 0.4. This is from for chromium doping. And the structural parameter, as we have already discussed, volume also here decreases with increasing chromium concentration due to difference in ionic radii of chromium 3 plus and manganese 3 plus. Here it is simple. Chromium 3 plus is having very small ionic radii, so there is no ambiguity of reduction in volume why it is so. A minus B decreases, and when the chromium concentration increases, and such decreasing trend clearly indicates the orthorhombic structure tends towards a more symmetrical structure. So for x equal to 0.4, O prime to O type orthorhombic structural transformation takes place. Then jetty distortion, as chromium is a non-jetty element, obviously it will decrease, but it decreases very significantly. 0.2 immediately decreases one order. 50% of jetty factor decreased immediately when we dope chromium. So considerable reduction in jetty distortion factor, it replacement of jetty active element Mn3 by chromium. This is the Raman spectra. One can see this with increasing iron chromium concentration. One can see the at 0.4 it is significant reduction in this jetty active modes, and they are completely suppressed. And this is indicating the drastic reduction in peak intensity, confirms the structural transformation from O prime to O type with reduction in jetty distortion. Similarly, the photoluminescence spectra is also showing the same feature. 286 nanometer peak is disappearing with increasing chromium. So that further confirm that whatever may be the non-jetty element when we add, the jetty distortion reduction can be seen from this 286 nanometer emission peak. And magnetic feature is very important in this case because as soon as we add the chromium, one can see very different feature we observe here. This is for 0.1, it is showing a similar TP behavior, but in 0.2, one can see the ZFC, FC, it is this FC curve, in fact, crossover the ZFC curve, which is very unusual feature. And this here you can see MFC minus MZFC, there is a minima which indicates the spin deorientation transition. And at different field, in fact, this crossover is clearly seen at 31K ZFC FC, the crossover. When it is 0.3, you can see this, there is a crossover and there is a maximum feature, and this minimum is spin deorientation transition. So many feature you can see when it is 30%. In fact, in 40%, you can see there is another feature is added to this, there is a compensation temperature. That means at this temperature, this the magnetization is 0. How come magnetization is 0 in this system? And it becomes negative. So there is a magnetization reversal, compensation temperature, and spin deorientation transition temperature. temperature. So all these feature we could able to see in when chromium is added, and this is at different field. One can see here how this feature is changing with decreasing temperature. One can see the feature like there is a peak, there is a compensation temperature, there is a spin reorientation transition temperature. This feature we could see in 0.3 and 0.3 at 50 Oersted and 100 Oersted. So why this is observed, that mechanism I will discuss, and this this magnetization reversal feature, in fact one can fit it into this formula where there is a internal H internal and H external field which we are applying. H internal means what? When we are cooling the sample in presence of a magnetic field, there is chromium, manganese and gadolinium, 3 elements are there. So when we apply a magnetic field, chromium align towards a magnetic, try to align towards a chromium or manganese, both align towards a magnetic field, and that chromium have some internal field it will generate. That internal field align the gadolinium movement. So there is a competition between chromium alignment, chromium or magnetic moment with gadolinium. Chromium and magnetic align with external magnetic field. Gadolinium align with the internal field arises due to the chromium. So that internal field we have calculated from the after fitting this. How the internal field, how much is the internal field is generated due to the chromium, that table is here. You can see this with different field, how this internal field is increases. And in 0.3 and 0.5, this internal field is increased with increase in field. So with increase in concentration also the internal field is high. And theta is of course the Curie temperature, which is negative, which shows the antiferromagnetic behavior. So this is another important feature, and this one can see in 30%. If we'll have 100 Oersted magnetization, we are cooling the sample, you will see this feature. Okay, the black one, FC. And suddenly at low temperature, when we'll apply minus 100 Oersted, immediately it reverses back. It shows just like a mirror. This magnetization behavior just like a mirror in 0.3 and 0.4. In 0.3 at 100 Oersted we see this feature, and in 0.4 we see this feature at 500 Oersted. Just we are reversing the field, we could able to reverse the magnetization behavior completely opposite. And that is a very important mirror image of magnetic properties which is used in spintronics. And this mechanism, one can see here how one can define this negative and compensation temperature is that, as I told, with external field, this manganese or chromium, they shows a canted behavior, and this shows a magnetic, weak ferromagnetic behavior, and this chromium produces an internal field, and that internal field is aligned the gadolinium in opposite direction. Because internal field always opposes to align the magnetic moment towards a magnetic field direction. So that internal field align the gadolinium in opposite direction. So this gadolinium and manganese, they compete, and it shows a peak over here at this temperature, and then gadolinium dominates, and it shows a 0 value compensation temperature when this manganese, chromium, this canted moment and gadolinium is exactly equal. That is called decompensation. And then with further decreasing the temperature, chromium remains same, but gadolinium increases because gadolinium also align at low temperature. So this is in the orientation temperature. Above that, again, it is increases. So this mechanism we have given for this behavior, why it is behave like a compensation temperature it shows, and a negative magnetization. So this magnetization reversal feature is very important for the application point of view. Similarly, other thing we have derived from this inverse susceptibility, like we calculate this theoretical value, and then the theta value which is negative, that suggests antiferromagnetic behavior, and then the switching behavior. It is another feature we observed in this material, that what we did here, we cool the sample with a magnetic field, suppose 100 Oersted at 10 up to 10K, and 10K we measure for certain time period like 1000 seconds. And then immediately within a fraction of second, we change the field up to 500 Oersted and we measure the magnetization up to 1000 seconds. So this is just a switching behavior with magnetic field. At 100 Oersted, it was constant. Immediately we switch to 500 Oersted and measure for certain time period. It is remains switched to another magnetic moment. So with this different field, one can switch the magnetic behavior. That is point. This is 0.3, and in 0.4 at 10K, we apply the magnetic field 500 and 1700 Oersted. As we increase the iron concentration, the switching behavior, in fact, it needs very high field. So this is again, we did this remnant magnetization measurement to find out the behavior like spin glass or not. All are showed spin glass like behavior from remnant magnetization with time. So this is all about the chromium doping with increasing X iron chromium concentration from 0 to 0.4. Along with reduction in lattice volume, we observe structural transformation O prime to O type orthorhombic. The Raman spectra confirm a significant reduction in jetty distortion factor due to this asymmetric stretching band 487 and 610. Emission peak 286 nanometer in PL spectra disappeared with reduction in jetty distortion. PL and XPS both confirmed the presence of Mn4 plus, and the PL study demonstrated the emission spectra emerging due to allowed electronic transition within Mn4 plus energy band. Both TN and T compensation increased with chromium doping. Switching behavior is observed in X equal to 0.3 and 0.4. Spin glass behavior observed in all the samples. This is just a very elaborative work. One student just passed out. She has done both different concentration dopant like iron and chromium. And so these are of course, her photo is not there. Her name is Priyanka Tiwari. She has already done this work and got the PhD. She is now PDF in IIT Guwahati. And these are the current students who are working. Another two students are not here. So, sorry to say, there is some voice in the background. Thank you.
Thank you very much for the nice presentation of Professor Chandana Madam.
Please tell somebody to not to.
Yeah, Madam. Some questions are there in the chat
But
box.
mute the audience first.
In the chat box, some questions are there, ma'am. First question is, what is the origin of the distortion, thermodynamical or electrical or mechanical?
Electronic, it is. Electronic degeneracy.
Next question is, why are we using the rare earth metal?
Rare earth metal, you can see all these features we could able to see in rare earth metal. So just to have different properties in different material, we could do this rare earth manganite system.
Next question is, why does the antiferromagnetic ordering increases with addition of iron, which is itself highly ferromagnetic?
Yeah, but iron is not behave like a single atom. Iron is going to manganese site, and iron is interacting with manganese. So that gives your antiferromagnetic interaction.
Okay, ma'am. Next question is, what
And
is
in fact, sorry, but iron is very small concentration. It is not 100% iron. Iron is 10-20%. So iron may not interact with iron directly.
If iron is 50% more, then it will
But
be
still,
interacted.
but still there is manganese is also 50%, no?
Yes.
So, like ferromagnetic feature is approaching, but it is not complete ferromagnetic.
Okay, ma'am. So what is spin glass behavior? Next question is.
Spin glass behavior is like glass, like the spins, they are not very ordered. Like in glassy behavior, the spins are like glassy behavior, but they freeze at low temperature. With temperature, these spins they freeze. So at certain spin freeze temperature, above that temperature, you can see this spin glass behavior. Below it may not be spin glass, it may be ferro or ferry or whatever. But spin glass feature is like glassy behavior. General glassy behavior we observe in amorphous material, like that is spin glass where the spins are not exactly ordered. That ordering occurs with temperature only, low temperature.
Next question is, what is the region of increase in Nil temperature with increase in temperature in this material?
What does it mean?
What is the region of increase in Nil temperature?
Nil temperature with composition. Nil temperature with temperature means what? Nil temperature is a temperature. With temperature it increase means what? It is not a valid question. Increase in Tn with temperature means what? Tn is not increasing with temperature. Tn is a temperature.
Tn is also temperature.
Yeah. Tn is a temperature. It is increases with temperature means what? It increases with some other parameter, right?
Yeah. Ma'am.
Hmm.
Next question is, why there is increase in Tn with iron increases?
Yeah, that is Tn increases with iron. Increase in iron means your Tn is what? The Néel transition temperature. Okay, Néel below Tn it is antiferromagnetic, perfect antiferromagnetic. But when iron is there, iron is not, as you told, it is why this antiferromagnetic ordering is increasing. That means what? Tn is increasing. So iron is not at a place exactly ferromagnetic ordering it do. Rather, it is having double exchange or exchange interaction with manganese through oxygen. So that increase this Tn with iron. We don't know up to what concentration we can increase so that it completely become ferromagnetic. Because it may not be ferromagnetic also, because FeO3 also is not ferromagnetic. Because gadolinium is also there, it is also a magnetic element.
Next question is, what does trigger John Taylor distortion?
That's what I discussed no initially. Antenna distortion occurs in when there is a degeneracy. If you have one electron and there are two states, that electron cannot decide which state it will occupy. So to lowering the energy, it will have a distortion. That is in fact called Ian-Teller distortion. Whenever there is three state, like I discussed in D1 state, it is have a possibility of all these three state it can go. So that is the degeneracy, and that makes the Ian-Teller distortion. All the element cannot be Ian-Teller distortion active, because if all these states are filled, then you don't have this Ian-Teller distortion. So this lowering of energy that triggered the Ian-Teller distortion.
Okay, ma'am. Thank you.
Okay.
So we have got all this information about chromium and iron doping in gadolinium manganese oxide. Means that is the
Samita.
perovskite material. Okay, sir.
Sir,
Hi.
namaskar.
Namaskar.
Chandana, it's very nice talk. I'm glad such a cutting-edge research talk you have given on the work that you are doing there. I just have one comment
Yes.
regarding a question that was asked. Iron prefers ferromagnetism. How does it induce antiferromagnetism? Actually, ferromagnetism, antiferromagnetism is not a chemical preference like iron is ferromagnet, nickel is antiferromagnet. It's not like that. There is a Slater's prescription. If distance between two ions come closer than less than the 3 times their radius, I'm sorry, the separation is more than 3 times their radius, then it will be antiferromagnetic. Less than 3 times ferromagnetic, less than 3 times it will be antiferromagnetic. Slater's prescription. So it's iron can be antiferromagnetic if you forcibly push it together to make the separation less than 3 times the R naught. It's a more of a physical effect than chemical effect. Same iron going into some other lattice can induce antiferromagnetism. As Chandana has seen.
Yes. That sorry, sir. That is a nice answer. Actually, I should have given that. When you have a ferromagnetic or antiferromagnetic, depending upon the distance between two atoms, if you will make it close, obviously the repulsive force has to be higher, and it will make it antiferromagnetic. This is Pauli exclude. Allow all this, you can make ferro or ferri depending upon the distance between these two atoms.
Okay.
Thank you, sir, for remembering that answer. Okay.
Yeah, very nice talk.
Yeah.
Very nice. Okay.
Thank you, Chandana.
Recently, we have that student has done, Priyanka. She has done all this, both chromium and iron doping. And chromium doping, in fact, we observe very nice features. And this is the similar work somebody has also is going to do in the same GD systems. Let's see what feature we are getting.
Thank you, Chandana. Thank you.
Yes,
for that talk. Very nice talk. Thank you for that.
Thank you. To you are at least remembering me and giving me this opportunity time to time.
You are permanent member for